Hello, my name is Jordan. I am a math and science tutor, and my favorite subject is chemistry. Today, we're going to be doing a quick lesson on electron configuration. So let's go ahead and get started. First, I want to be sure we understand the periodic table a little bit. So let's look ahead and define a period and a group. A period is going to be going vertical along the periodic table. So this would be period one, period two, three, four, five, and so forth. And period is going to be, so run vertically along the periodic table. And this is going to define our energy level. So the first period would be n equals 1, second period would be n equals 2, and so forth. So we would say lithium and carbon are period 2, or n equals 2. And then we have groups which run horizontally across the periodic table. So hydrogen is going to be group 1, beryllium is group 2, helium is group 18, boron is group 13, and let's fill these in accordingly. So we would say a group defines our number of valence electrons. So we would say, in this case, helium has 2 valence electrons. But then let's look at neon. Neon is group 18. Neon is going to have 8 valence electrons, group 18. Lithium is going to have 1 valence electron, that's group 1. Carbon is going to have 4 valence electrons. That's group 14. And so let's look at defining from these energy levels, kind of breaking them up into subshells and orbitals. So let's look at our subshells. We have different types of subshells. We're going to have an S, P, D, and F. And these are important because these subshells and orbitals are where we can estimate an electron's location. And we use the periodic table to kind of define these subshells and orbitals. So an S subshell is going to have a spherical shape. A P is going to have a dumbbell shape. A D is going to have a clover shape. It's going to be 2 overlapping dumbbells. F is going to be a little complex. It's going to be overlapping dumbbells. And F is pretty unique. And then let's look at the number of orbitals. So for S, we would have 1 orbital. For P in an energy level, we could have 3 orbitals. D, we could have 5 orbitals. F, we could have 7 orbitals. And an orbital contains or can contain 2 electrons. So the maximum electrons in an s orbital would be 2. Maximum in a p orbital or p subshell would be 6. D subshell would be 10, and F subshell would be 14. And we can use this kind of shape and these notations to define how many electrons or where electrons would be for a given element. So let's look at hydrogen, for example. Hydrogen has 1 electron, and it's in the first energy level, so N equals 1. It's the first energy level. And we always will fill in order of lowest to highest energy. And our lowest, simplest orbital is going to be S. So we fill S first. So hydrogen is notated as 1s1. So then if we look at helium, that would be notated as 1s2. Because it's going to be 2 electrons in that first S orbital. And let's look at lithium. Lithium has 1, 2, 3 electrons. And so we fill the 1s2, and then we say 2s1. And that's going to be our electron configuration. Let's look at carbon. Carbon, we have the 3 from lithium. Let's keep going. 4, 5, 6. Carbon has 6 electrons. How many valence electrons? It's going to have 4 valence electrons. So 4 VE. So let's just make sure we know that. So let's fill in. We fill we fill the 1s, right? And then we fill the 2s. So 1s2, 2s2. And then over here, let's define this a little bit more granularly. This is going to be our p orbitals. So carbon begins the p. So what we would have 2p2, because we have 1, 2 electrons in that p orbital. And we make sure, let's define the periodic table in terms of orbitals now. So group 1 and 2 will be our s orbitals. D is going to be this middle portion. And then down here is going to be our F orbitals. F orbitals are very unique. We will talk more about them in a later video. So then let's look at going from electron configuration to looking at a little bit more of the orbital diagrams. So this here is our electron configuration. So now let's think about orbital diagrams. So we take this notation and now we think about actually doing kind of like a representation, a visual representation of electrons. So we we can call it box and arrow diagram as well. Orbital diagram is the correct term. So we have one box is 1 orbital, 1 arrow equals 1 electron. So two arrows, right, would then be two electrons. Let's make sure we understand that foundation. So let's look at carbon again. So carbon, we said is 1s2, 2s2, 2p2. So let's look back. We have 1s, 2s, and then how many p orbitals do we have? We have 3. So let's draw our 3p orbitals. And this is still going to be in the second energy level, 2p. So now let's think about filling this. So something important we need to remember is light charges repel. So two electrons will be opposite of each other. So two electrons will repel. So we can notate this orbital diagram with electrons. Let's fill it in. We have 1s1, 1s2, and so forth. And then when we get to the p, we're going to go up, up. And so let's define a little bit more of why we did this way, because this would be correct. But we also could, you're maybe thinking, why did we not do it like this? If you want to fill lowest first, that would be not correct. This would be correct. So let's define some of our rules. We have the off-bow principle, which states that we must fill the lowest energy level first. Fill the lowest energy level first, which makes sense. And we did that, right? We fill our S, so fill the S, then P, and so forth. And then we have our Pauli exclusion principle, which states that each orbital can only hold 2 arrows. Okay, so my last video got cut short a little bit, so I'm just continuing on. Kind of the last minute of the previous video can be cut out. I'll try and edit it. We'll see what happens. Okay, so let's explain a little bit why. So let's explain a little bit why we did the orbital diagram this way and how we do orbital diagrams. So, right, continuing to look at carbon, let's define some rules for orbital diagrams. We have 3 rules. We have the off-bow principle. We have the Pauli exclusion principle. And we have Hund's rule. The off-bow principle states that we must fill the lowest energy level first. Which we did. So, right, first fill S, then P, and then, right, we also have to fill N equals 1, then fill N equals 2, in that order. So then let's look at the Pauli exclusion principle. And this is going to state that an orbital holds at most two electrons, and those two electrons must point in opposite directions. So one orbital holds two electrons. They must point in opposite directions. And then Hund's rule is we must put an electron into an equal energy box before putting a second arrow in that energy box. So we fill um, equal p orbitals before filling two electrons in one box. And this would be any orbital. We fill any orbital before putting two electrons in one box. So, right, when we look at our 2p orbital, we do this, not this. So we fill each p orbital before doing two electrons in one p orbital. And so let's look at an example. Again, let's do magnesium. So let's look at magnesium. Magnesium is going to have 12 electrons. So we would fill first. Let's notate we have 1s, and then we go to 2s, and then we go to 2p, and then we go to 3s. And so we would, if we have 12 electrons, we fill our s orbital. So we go down, we fill our 2s. And then to fill the p, we go up, 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 down, down, down. So that's 2, 4, 6, 8, 10, and then 12, up, down. And that's going to be magnesium. So we could also the configuration. So this here, configuration, this orbital diagram. Configuration would be 1s2, 2s2, 2p6, 3s2. And maybe you're thinking this is a lot to write. It is. So we have something called the noble gas configuration, in which it's kind of like a shorthand using the noble gas in the previous energy level or period. So let's look at magnesium on the periodic table. Here's magnesium. Let's go one period up, period 2, or N2. Our noble gas is going to be neon. So that shorthand notation can be done as such. In brackets, neon. And then we would just pick up at n equals 3. So 3s2. So that is a good tool. It's good to know that the difference there between the electron configuration and then noble gas configuration. So let's go one step further into a little bit of quantum numbers. Quantum numbers are useful because this is kind of like defining, it's used to define the location of an electron. We can also think about also can define the energy states based on a set of quantum numbers. So we have 4 quantum numbers that we use. We have the principal quantum number, and this is the energy level. So it's notated as N. It represents the energy level. And then we have the angular momentum quantum number, angular momentum quantum number. This is notated as L. I kind of like it angular. I think about this L, angular. And this defines the shape of the subshell. So this is just different ways of notating SPD and F. So if we have S, we have L equals 0. If we have P, we have L equals 1, D, L equals 3, L equals, if we have D, L equals 2. If we have F, L equals 3. And then let's look back to the principal quantum number. We have N equals 1, 2, 3, 4, and so on would be examples. That's going to correspond with the period typically. We have the shape of the subshell defined. Now let's think about these different orbitals, right? If we have S, S is going to have one possibility. So S has one 3D orientation. We said P could have 3 3D orientations. D could have 5 3D orientations. And F could have 7 3D orientations. So these 3D orientations of a specific orbital is going to be known as the magnetic quantum number. And this is going to be ranging from negative L to L. So ranges from negative L to L, and it defines the 3D orientation that an electron could be located in. Again, it's kind of like a zip code. You know, maybe this is your street. So it's kind of giving us specific information on where the electron is. And so for S, because we only have one orientation, L is 0, right? So L could equal or is 0. For P, we have L could be -1, it could be 0, and it could be 1. For D, L could be -2, it could be -1, 0, 1, and 2. L would be -3, 2, 1, 0, 1, 2. So we take that, and this is going to define magnetic quantum number, which is notated as M sub L. So M sub L. So M sub L is magnetic quantum number. And so magnetic M sub L, right? Because we use the angular number to define the number of 3D orientations in a specific orbital. And then lastly, we have our spin quantum number. And this is defining the electron spin, which could be only up or down. So that's going to be two possibilities. Up or down, notated as positive 1/2 or negative 1/2. So that's going to help us identify the kind of specific location of an electron. So if we look at back our example of magnesium, let's try and define quantum numbers. So, right, our possible numbers are N, L, M sub L, and our spin number is M sub S. And our spin number is M sub S. So the energy level for magnesium, right, we said was N equals 3. N equals 3. So let's continue on. And then it's going to be in the S orbital. So N equals 3. L would be equal to 0. M sub L would be equal to 0 again, because that's the only option. And then M sub S would be equal to, we could add either a positive 1/2 or negative 1/2.